All right, in this video we're going to look at some OWL problems. I'm Dr. Hayes, and this is Andrews University Chemistry, and today we're going to look at just some overview of the type of problems you're going to do with free energy, equilibrium constants, and free energy dealing with enthalpy and entropy. And you're going to really have to need to know the difference between delta G and delta G naught. These differences are important. So you'll often see it like this, and we'll discuss them as we get to it. So the first problem in OWL is dealing with the equilibrium constant and delta G naught. And since they don't have superscripting, it's really delta G naught this way. So here's a standard problem using the thermodynamic tables up here in the references. You can click and go find your thermodynamics and your delta G's. You can calculate the equilibrium constant for this reaction. This is to get your knowledge to test how you can use delta G naught, and you're going to sum up the free energies of the products minus the free energy of the reactants. Products minus reactants. These are the formations, so you're going to go look these up in the table. Once you've got your delta G naught, this relates to your equilibrium constant, whatever the equilibrium constant may be, and then you got to solve for K. So that means dividing both sides by RT. And then once you get that, you'll take the exponential function to undo the natural log. So really, K is equal to the exponential function minus delta G over RT. So these are the things you'll be looking for in this. All right, so that's problem number one. And units are very important, as always. So we're checking for that. Second problem is going to go the other way around. So if you know what delta G is and you figure out the equilibrium constant, how can we go the other way? So in this one, the equilibrium constant is given for this problem right here. Oof, it's a huge number. And so based on this value of the logarithm, what do you expect delta G? So there's a connection between delta G and K. Essentially, if K is greater than 1, then delta G is going to be less than 0 or negative. K is less than, how about we go to eraser here. If K is less than 1, then delta G will be greater than 0, will be a positive number, and that will be non-spontaneous. So that's why we're trying to teach you these connections here between all the different numbers. So, man, that's huge. So much greater than 1. So we're going to be dealing with this scenario right here. And that's why they're asking you for the relationship to 0. And then it says calculate the free energy change for 1.63 moles. And here is the equation once again to deal with the relationship between equilibrium constant and delta G. So this one you can just plug in the equilibrium constant multiplied by the temperature in Kelvin, which is given, and then R is the 8.314 joules per mole Kelvin. So just testing your knowledge there, but that gives you the delta G for per mole. So then you're going to have to multiply it by the number of moles to actually get the energy there. All right, so that's problem number 2. And number 3, let's see, the equilibrium constant from enthalpy and entropy. So right away, I always think about the relationship between the enthalpy and the entropy here to free energy. So these numbers are given, so I can go right into the free energy. But what do they want us to do? Oh, they want to know the equilibrium constant for this at 263 Kelvin. So we're going to have to use that number here to get us the free energy. And then once we know what delta G is, we can go back to this equation right here with our new temperature, okay, and solve for K, and determine what K is once you have the delta G. So you're going to have to solve for that, just like we did before in the earlier problem. Okay, kind of going at it from a different angle there. All right, number 4, calculate which temperature at which the equilibrium constant is greater than 1. So that's what we're going to look at in this problem right here. The equilibrium constant Kelvin would be greater than 1 at temperatures where? So a big understanding on these type of problems, especially when you're given your delta H and delta S, when the signs are the same, especially in this case for delta, for the enthalpy and entropy, there is a temperature dependence for delta G. And so that there is a crossover between non-spontaneous and spontaneous. It's going to go through a point where delta G is 0. So we're going to have to solve for that point using this equation right here and solve for T when delta G is 0. So let's put a little line in there so it doesn't look like an O. And then once you solve for that temperature, you're going to have to think about which quadrant this falls under. And please go back over my notes and look at this thing about quadrants here. And these two right here are temperature dependent quadrants for the 4 types of chemical reactions that occur based on the delta H sign of enthalpy and the sign of entropy. All right, number 5, we're getting into see if you can recognize the difference between delta G and delta G naught. Okay, so this is at standard temperature and pressure, and this is at non-standard temperature and pressure. So using the thermodynamic table above, figure out the delta G for this reaction right here at 298.15. So this, at first you want to figure out what delta G naught is. This is using the tables. So this could be done probably using the summation one, the products minus delta G on the formation of the reactants. So that's P. And once you get that, that's an important part. And then the new delta G under non-standard conditions is equal to the delta G at standard conditions plus RT ln of Q. So our goal then is to, once we've got delta G, is find what Q is. So Q is the equilibrium expression. You have to square that over the pressure of N2 squared and times the pressure of O2. So we're going back to equilibrium theory, and it says, well, here the pressures are given 10.58. So maybe switch that to atmospheres, and then N2 and O2 are at 1 atmosphere. So you keep those at 1, but it's got to make the same units here. And once you get them in the same units, you can just plug them in to these parts right here. That will get your Q. And then don't forget what R and T are. And your delta G. Hopefully that's some help there. Calculate K at different temperatures. So what's this problem? Equilibrium constant at the following reaction is 0.63 at 600 Kelvin. If the delta H for this reaction, what is the value of Kp? So what's interesting here is they're giving you the delta H and the equilibrium constant and a couple different temperatures. This is going to be dealing with the Van't Hoff equation, and I'm just going to make a separate video for this. So we'll call that one lecture 49A. And it's not too bad. We've encountered this type of an equation before, but I want to give it its due process here. So we'll look at that. And you can obviously get some help from OWL on that. And the last one, I didn't really have any lecture on, but it has to do with free energy and work. And work here, W, is defined as the opposite in sign of whatever you would calculate for delta G. So they basically in here want you to figure out something to do with that. Let's see. The maximum amount of work that can be done by this reaction when 1.63 moles react at standard conditions at this temperature. So the amount of work that can be done, well, they give you delta G right here, and we can understand that to be minus 449.1 kilojoules per mole of the reaction. And since there's 1 mole of tetraphosphorus decaoxide, then if I have 1.63 moles, then my moles can cancel out to give us what we need. So that's per 1 mole of the reaction, but 1 mole of the reaction is 1 mole of P4O10. So really, we should complete that out there. Okay, so hopefully that gives you just some quick guidance on how to get started and quickly assess these problems that are going on.